Good morning, everyone. Before we start, we'd like to acknowledge the University of Waterloo, where much of our work takes place in the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated in the Haldeman Tract, the land granted to the Six Nation that includes the 6 miles on each side of the Grand River. Our active work towards reconciliation takes place through our campuses, through research, learning, teaching, and community building, and is coordinated within the Office of Indigenous Relations. Today, is a much special day, as you know, today is the Truth and Reconciliation Day, which is celebrated across the campus. Hopefully, you will find time today to be part of those campus activities along with the talk that you are hearing today. So we are really fortunate to have Professor Thomas Thundat, who is coming not that far away from University of Buffalo. And Thomas has been the Canada Excellence Researcher, CERC laureate at University of Alberta from 2010 to 2017. And I think a few of those years I had the fortunate to overlap with him. And prior to that, he was a corporate fellow with the Oak Ridge National Lab as well. So he has a distinguished career. I will not go through his entire achievements, but I think it is quite fortunate that we are having Thomas spending the time here this afternoon with us, though it's a very short trip for him, but hopefully he will continue engage with us in various fronts. So, Thomas, the stage is yours. Thank you.
Around 20 years ago, I went to South Dakota. Somebody came and told me that they have this dog who can smell cancer. It's not possible. Then dog became part of my life. So thank you, Sushanta, for inviting me for this lecture series. We have a nice place here, got a nice tour. So I'm going to talk about the little bit about the dog, what it is doing. Because if you look at the vapor pressures of different gases, like a TNT, RDS, so on, it's extremely small. One core is 1 millimeters of mercury, 0.13 kilopascal. So that's not more to the run. So this has been the biggest problem because these dogs are not telling us their secret. Some they don't speak English. They don't speak dog language. What are they doing? So I went to a general book camp sometime back when our soldiers in Bosnia. All the dogs trained in the US couldn't detect any landmines. You can have a landmine sitting in the front, dog will come around with nothing. But generals are very smart guys. They're not scientists, but they said, hey, your dog is not smelling TNT. It is smelling something else. Why is it? And then they figured it out that these dogs are basically not sensing TNT instead of the other volatile or compounds associated, which are the higher vapor pressure, like limonene, acetone, toluene. So this is their secret. And they don't inhale, they are actually exhale. And we kind of figured out lots of different things about the dog, and I will keep coming back to this thing. On the other hand, our noses are actually pretty good for lots of things like phenol, 1 parts per million. That's ppm. But if you look at the vanillin, for example, was in the mass, we can detect 10 to the power 1 part in 10 to the power 13. It's unbelievable. I have no idea what is the evolutionary mechanism for this. So remember that this is ppm. And we are detecting extremely small amount, some of the chemicals. Sometimes when we become chiral, we have a hard time. So we don't understand how the olfactory works. You know. And if you look at the long time ago in China, India, Greece, and places like that, when you were doctors will smell you. Yeah. Because they know from the smell what type of disease you may have. From their practice for years and years of experience, they can tell what type of disease most of the time. And there are lots of activities going on right now looking at the what are the VOCs associated. So we can actually, maybe at home, we can actually figure out maybe it is nothing, right? Or the profile changes completely, and then you can go to a doctor and say, okay, this is what is something is wrong with us. So molecules are a big market. You know, chemical sensing, biological sensing. Sensing is the biggest market available there. One of the misunderstandings of this kind is that there are sensors out there that can detect, which is not true. Absolutely, there are specific sensors available, but not that will cover almost everything, basically. So you may have grown up with Star Trek from old days. So young people may not know this thing. And so there is this Star Trek, there is a tricorder that I can detect everything. There's a handheld device going around, so people have been trying to figure out how do we make a tricorder. There are lots of people trying it, and or have been trying to come up with. So it has to be handheld. It has to small, high molecular specificity, you know, detect biomolecules, physical things, chemical things, rapid detection, fast integration, everything. But unfortunately, people have not been successful coming up with it. But this is still a goal whether we can detect something, everything actually, using something more enough that can be carried around. We were also intrigued by other people's work on this area, whether we can make something like this. So there are lots of chemical information floating around, you know. Basically, this is taken out of Kunst's talk, basically, the chemical profiles around it. You know, in the indoor air has over 300 different molecules floating around. Human body produces, it was 400 when I was at Oak Ridge, and nowadays it's 1,800. It keeps going up. The amount of VOCs produced by our body are going to 10,000. These numbers will keep increasing as our sensitivity of detection starts increasing. Uh, Ambient air has lots of water. This is another complicated factor. Water. The, the water vapor pressure, water, there are parts per thousand, lots of water. And they are, unfortunately, they have a huge dipole moment. They stick to everything. So whatever you want to detect, we have to deal with water. So most of this electronic nodes and process basically fail because of the water. Water is the biggest problem, especially when it is appearing at a high concentration. So this is the way sensors work. Most of you may know. Then basically we have to collect molecules and then absorb some kind of a transducer. And remember that all of the chemical sensors are physical sensors. There is nothing like a chemical sensor most of the time. All of them are physical sensors. When the molecules are absorbed on the physical sensor, it changes one or more properties, physical properties, maybe absorbed mass, mechanical properties, thermal properties, optical properties, anything physical that you can measure. So that it doesn't really detect molecules. only way we are doing is that we will make a chemical interface or some kind of a receptor that can bind to that molecule. And that's what I will be focusing on, how we're going to overcome that problem. Most of the time, it may be polymers, self-assembled monolayers, nanomaterials, nanoparticles, or biomolecules, enzymes, proteins, so on. So there's an array of things that is available. And most of my work focus from nanomechanics and approach uh, still going on. So the cantilevers are easy to make and with clean room you can make it easily always. You can make it a piece of resistive fashion, so it's a hard electronic readout. You can make it smaller and smaller. Few micron size to all the way to 500 micron. Okay? The cantilever, the beauty of the cantilever is that it gives you multiple signal at the same time. Multiple signal. It will give you the frequency coming from mass loading, assuming molecules are absorbing on the surface, and the mass changes, and it can detect that. If we confine our molecular absorption to only one surface, then surface stress changes. So differential surface stress makes the cantilever bend. It has nothing to do with gravity. You know, solids also have surface tension, what we call it surface energy, basically joules per meter square, which is basically nothing but the Gibbs energy per area at constant temperature and pressure. You see, in addition, we also see changes in the amplitude, phase, Q factor. But the first two things, frequency and bending, are the easiest one to detect at this time. And the equations are very simple. I can simplify this thing. Of course, you can add more and more. So basically, you have to remember that change in mass is proportional to change in frequency, and that's the original mass of the cantilever divided by the original frequency. And the bending is related to surface stress divided by Young's modulus and the geometrical factor which will enhance the bending. So if you make the cantilever longer and thinner, you get a better signal. That can be easily measured. This is one example from a long ago. So this is PTM, which is explosive. Is actually we send the vapor to the cantilever, and we are measuring two things at the same time: cantilever bending as well as its frequency. And frequency comes from Brownian motion. The cantilever is always going like this because of thermal energy around it. So all these dots you see are frequency measurement. Basically, what we do is that we look at the frequency back and forth. Look at where is the maximum potential, and that's the kind of how I look to be spread because the more you take the sampling of the frequency, you get a better result. And the red line is the cantilever bending taken at the same time, and you can see that they follow each other pretty well. And if you know that, like I said earlier, the bending is related to absorption energy, surface stress, and frequency is related to the absorbed mass. So if you do the manipulation a little bit, you can get the absorption energy per molecule, and it comes out to be pretty good. So it is a nice analytical tool actually. How much, what is the absorption energy per molecule out of this thing. For this material, I think we got 18 kilocal per mole. So that's pretty close. Very simple technique, you can get the real value. And here is a idea that we have shown lots of different type of methods that we can detect. But can we do it simultaneously? This is for an array of cantilever, all piezo resistive 32 of them. Actually, it's from Anya Boysen, who gave the talk here last year. So, from our collaboration, and we can actually deposit the different type of self-assembled monolayers over polymers and look at the pattern. So this is a way this evolved. Initially it looked like this, then it became like this, and even then we can tiny little capsule that can actually drug it. So I thought this is an excellent goal, basically converting this idea into a tiny little sensor that can basically give you all the information. And I will show you this a little bit later, how the result out of this thing. But we run into a problem. I will use the same thing. Problem is that still it's not selected. But why? One molecule, one kind of molecule. But when there are other molecules around, the confidence level goes down. If the two, the confidence level is only 95%, and if you have three, confidence level is 18%. And if you have more, the confidence level is not much. It's become practically useless. So the reason is very simple, because we use the idea that molecules, direct molecules, we have a cantilever, we have a receptor molecule, or a polymer or something, absorb that molecule. But we want this sensor to be reproducible and regeneratable. That means once the analyte is taken away, the cantilever should come back. You don't want to have a dosimeter where you throw away things like a biosensor. So basically that means you have to use something that is can dissolve at room temperature, that is KT, thermal energy. Right? So it should be physics solution and van der Waals interaction or hydrogen bonding. That's what we most of the time use. We can go up in energy in transfer reactions and acid-base reaction and so on, but then it doesn't dissolve. Then you have to heat it. The heating is a bad idea. It doesn't really work. For example, mercury absorption, gold is an excellent for absorbing gold. Of course, it also works, the endorphins come from sulfur. But if you heat it up to say 150 degrees centigrade, gold will dissolve. Hydrogen sulfide, which also interferent, which even 450 degrees centigrade. So, but you don't want to heat the cantilevers, because after some time they started bending around and then all the results become unreliable. So maybe we thought, okay, we can use the idea that we use hydrogen bonding and make an array and then use machine learning. So this is the array again, we coded with the different things, and only 4 cantilevers are shown here, A, B, C, D, trained with acetone, ethanol, water, TNT, only unknown vapor. And remember that there are 32 of them. And all exposed at the same time. And then we send it to some machine learning type technique, and this also fails. After some time, it doesn't work anymore because the of the binding is still hydrogen bonding. You can call different molecules or different type of interaction, but unfortunately, this approach also failed. So I was reading an article, actually, it's an old 20-year-old article written by David Wald. So David says that, that wake up and smell the coffee. This is not going to work out, right? We can have a sensor, let's say, for example, a cantilever array I showed, and if you want to distinguish between 2 different wines, Burgundy wine versus Bordeaux wine, you can see Coke versus Pepsi, which is better. Frame it with Coke, ready to test it and bring hope into the but it is the big cell that's the problem. And there are other things around. This doesn't work, you know. So this is a frequently asked question that people ask me, you know, why are you still doing cantilevers? You know, many different companies started, Anya started one, Anya Wilson, and we started Graviton, protein too. But all of them went belly up. Then again, balance of so that's what I wanted to have a discussion with you guys on it. How we can, I mean, is this still relevant? You know, the thinking about mechanical sensing and oh, so physical sensors, like I said earlier, they are physical sensors. They are well developed. I mean, that's what people use for transportation and machine learning, all those things. Physical. Chemical sensing, lack of chemical selectivity, lack of reproducibility, lack of sensitivity with the chemical tastes only, lack of dynamic range. So the biggest one turned out to be reproducibility. You know, we can have the lab, we made hundreds of cantilevers, scientifically, and basically did the experiment, and it did have a delta type response. It has a distribution of the response, so that means it doesn't really work. You know, sometimes some of the cantilevers are working very well, some of them are not working well. This is kind of all over the place, and we couldn't figure it out why. Only reason, I mean, when we look at the very few less that if you put a goal, depending on the way you prepare it, it can be big grains, small grains, and if you put a tile molecule, you know, it can be all over the place. Maybe the coating may not be uniform. Even big hole on a small cantilever is a big deal. On a QCM, it's not a problem. It's not nice. Even if some big hole happens, it's not a big issue, maybe 1% issue. So we thought through this little bit. How do we overcome the reproducibility challenge coming from mobilization? You know that microfabrication by itself is fine. 1%, less than 1%. Then you can like same properties. But it is a chemistry, it's a problem. How do you do the chemistry? So then we realized that cantilever is a very nice thermometer. It is the best thermometer ever invented in the world, right? It's a tiny little guy. You can get a temperature sensitivity 10 millikelvin at room temperature. You push a little bit optimization, you can get 3 millikelvin. That's background. And it's uncooled. It is very different from detecting photons, you know, like energy from infrared or something like that. No cooling is needed at all. And this is the taken out of actually references. This thing is taken out of Arun Majumdar's paper, basically. Yeah. Uh, Easy to model this thing. So we take a cantilever, deposit some gold on it, and then expose it to radiation from a monochromator that goes from 200 nanometers to 900 nanometers. We have a mercury arc lamp as a source, and you can see this is where the cantilever bending. How beautiful is this diagram? Unbelievable, the cantilever is moving up and down. As you can see the entire spectrum of mercury. No clear Lambert principle. It is the heat generated by the absorption of the light by some defects or something on the cantilever. And it blows our mind away. You can detect spectroscopy. You can have spectroscopic signals. Basically, looking at the bending of the cantilever. So again, equations are very simple. Change in temperature is proportional to how much the candle is bending, and even this Young's modulus of the first element in the bimaterial cantilever always coefficient of thermal expansion, just like a thermostat. When you take the heat, thermostat went up. What is exactly happening here? So if you look at the infrared spectrum from say 2 micron to 14 micron, this is called the molecular filter regime because there are no more. On the other hand, if you look at the near infrared, these are overtones, mostly overtones. So they have unique spectral signature, all these bonds. So we try to take advantage of this thing and take the cantilever, bimaterial cantilever. Usually we put TNT, and you can see that TNT spectrum look like this. Again, remember that this is a cantilever bending. This is the wavelength. Then we put PTN on it, the vapor phase, and then look at the cantilever bending. You get another spectrum, and you mix them together, send two different vapors, and you can see it looks like a linear combination of these two spectrums. So this is why infrared spectroscopy is so powerful that molecules don't care who is vibrating what. They are all linearly independent. And you can do the spectral matching, even if you have linearly compounds at the same time, you should be able to see it. The only thing we need is that you have to expose the cantilever one wavelength at a time. Or you can have an array of the cantilever and disperse the whole wavelength across an array of cantilever. And this is, we did it with what we call the naphtha. So this picture on the top is actually, it is a little glow bar, and a filter wheel that goes in front of it, changing the wavelength. And you can see that the cantilever bending, we call it, photothermal cantilever deflection spectroscopy, and you can see all the peaks. Remember that this is the picogram amount of material absorbed on the cantilever. And this is the ATR and the FTIR. You need a lot more material and a bulky detail. That's so important. So this cantilever can basically do the exact same thing, but picogram amount of material absorbed from spectrum. And naphtha, this is the naphtha. Naphtha is a complex molecule. But if you look at the spectral matching, you can identify all these peaks. Another example, look at the PFOA. Now we have lots of interest in PFAS. So PFOA is one of the problem one. Again, we absorb the PFOA on cantilever, and then looking at the cantilever bending as a function of different wavelength, and you can see all the different peaks. And this is the NIST spectrum, standard spectrum of PFOA. And we can identify all these things. And we can see that there are more features that we can see with this approach than conventional FTIR. Let's look at another example. This is a nanowire, it's a BFO nanowire. So it's not a cantilever, it's kind of a bridge going from one electrode to another electrode. It is suspended, and you can actually absorb molecules on it. And in this case, I believe it's RDX, which is an explosive, and that is one is the red lines. The red curve is but it is done not mechanically; it is done electronically. The readout, and look at the FTIR spectrum, which is a little broader and also not that sensitive. And so, if the thermal mass of the, especially since we are calorimetry, measuring heat, lower the thermal mass, the higher the response. So, making it smaller, making it much better. So, we were able to get 10 femtograms of RDX absorbed on the surface. we can go even smaller, So this is actually a cantilever. It has two different metals that come up to the tip. At the tip, these two metals come together like thermocouple. And the area where they are meeting together is 25 nanometer radius. So now when we started to do the cantilevers at micron size, 100 micron, 200 micron, we thought of a nanowire, smaller area. Then we giant cantilever, the tip of the cantilever. If you guys use radar, you know that how small is the tip of the cantilever. So the tip of the cantilever is the two metals coming and joining, and then this is the Seebeck effect. So it depends only on the source temperature and the cold temperature. It doesn't depend on the time. But you can have heat somewhere here also. It doesn't matter at all. Only thing the junction and the other two parts, cold and hot. Oh, these are hot, this is cold. It's two different Seebeck materials. So basically it is a different simple equation. And then we absorb different materials like a TNT. And so if we go to AIM, pick up some, deposit some TNT and then bring it to our IR and you get the spectrum. So we have done with the different DMMP and all different type of molecules and show that these actually works. So you can go to smaller and smaller level, detection possible. And then we run into another problem. And I came here to tell you the problems. Okay. So what is Achilles heel is or any kind of nonsense? The small surface area is the biggest Achilles heel. Nobody will tell you this thing because, we do data experiment. QCM, 1 nanogram per centimeter square. So this is what most of the time we publish, so our candidates can see picogram. But we don't tell you in terms of picogram per centimeter square, how many gram per centimeter? As the sensor gets smaller and smaller, you need a lot more material on the to detect. That means you have to have lots of molecules around your nanosensor. Nanosensor can detect one molecule or a few molecules, but you have to have lots of them around. Otherwise, the chance of detecting assuming parts per trillion or parts per billion molecules in that ambient, the chance of them absorbing on that function area is very, very small. People use pre-concentrators to overcome this problem. So we'll talk about the pre-concentrator. So every surface is a pre-concentrator, right? Larger the area, molecules. So even if it's appearing at parts per trillion level, some molecule will touch somewhere. But whether it happened to be on your sensor or not, that is a question. So this is the ppb parts per trillion here per cubic centimeter. Depending on the interaction between the molecule and the surface, you can see you get the monolith on the surface if you have a strong absorption. So this is how do you get strong absorption? Of course, you have the heat of absorption here and surface energy. That's what matters. So high surface energy materials like metals and things like that absorb more, polymers and things like that. Low surface energy may not absorb that much. So people have developed, this is from my collaborator Sean Lim in South Korea. He makes all kinds of pre-concentrators that can, here has a hierarchical structure, metal form, and then more on the top of it. So the pressure difference drop across the inlet and outlet will not be a big problem. And then, so this is, it works well. Most of the pre-concentrators can do 100 or 1,000 times, but it takes time. Enough of time is too much when you use a pre-concentrator, when you have the molecules up here at a really, really low concentration. The lower the concentration, you have to sample the whole air to get some few molecules, right? So again, this is a problem. You want a real-time detection. If you use pre-concentrator, it is not real-time. This is where we developed another idea called molecular antennas. The antennas are basically like electromagnetic wave. You can have a bigger antenna and you get a feeble signal coming from it. You focus it to the center point and or focal point, and you can actually detect the feeble electromagnetic waves. Can we do that with this nano sensor? Yes, we can. So what mistake what we did, we wanted the molecule to be absorbed by a nanosensor. And I told you nanosensors are physical sensors. They are not chemical sensors. So if we have a say parabolic dish, like a O-axis parabola, and let the molecule absorb on it, and we excite the molecules with infrared light, and the light is then focused to, say, for example, the focal point. We can actually use a cantilever, the optical beam detection system. So you could sampling a whole area, whole area. The your nanosensor is a physical sensor. It is supposed to be a physical sensor. Yes, it's a physical sensor. But all the chemistry is happening somewhere else, absorption. So we separate the absorption area from the sensing area. And this was excellent concept. So we said, okay, let's test it out. And here we go again, PFAS, absorbed on the surface. And then you can actually, you can see this is the cantilever response here, showing here. And this is a wave number, and you can actually detect all the different molecular vibrations. So basically, you are increasing the area of the sensor indirectly, and so even if it is a concentration is extremely small, you can still detect it. We have shown with this approach, we can detect parts per trillion level molecule right away. In real time. You don't have to need a pre-concentrator because pre-concentrator is built on the system itself. So it shows that here our light beam was smaller. And actually it's a beam expander and expand the whole surface area. Of course, we can also collect all the photos at the center again at the focal point. So this is some of the amplification that we have seen because it's a little more than the basically the area. There's something else is also happening. Because if you look at the molecular vibrations, they have vibration and excitation, and the excitation happens within 10 to the power minus 14 seconds. Optical sense, not 10 to the power minus 8 seconds. So vibrations they relax very fast. So maybe I forgot to tell you where is what happened before the cantilever is bending because when you excite the molecules start vibrating and they produce heat, and that's what the cantilever was detecting, right? So there is no coating involved, there is no chemical functionalization, nothing. It's a plain surface, molecules are so, and you excite them, they get excited, they relax, and during the relaxation, there is what you call the non-radiative heat transfer, non-radiative decay. That is what the cantilever is detecting. In this case, the also produces when the vibrational excitation, the excitation can be radiative and non-radiative. Here we are looking at the radiative path and the radiation coming from the molecule and picking it up. So it's two different approaches. And here we have the some PFOA. Again, remember that it's physical, no chemistry involved. And then we look at that. How does it dissolve as a function? And this is the time here, how much is evaporating away. disorderly. And we calibrated all these things with the QCM. Of course, QCM cannot go that low. So we have to extrapolate. So once you have an extrapolation curve, we can detect how many molecules are absorbed on the surface. We have also done other molecules other than PFAS and so on. DMMP. DMMP is a simulant for Saturday. Remember the Tokyo attack in 1995. So we can absorb the DMMP on this molecular antenna and excite it with a different IR wavelength, focuses on the focal point, the emitter radiation, and we pick it up with the. So this one works very well too, and again, very high sensitivity. So you may ask the question, will it work with, for example, mixers? And there you go, the mixers. DMMP and PFOA together, and there are two different. Blue is DMMP, and the orange color is PFOA, red one is the mixture of these two things. So I have shown that it works. The story gets much better now. Remember that I kind of alluded to it earlier. There are curvature effects. You can have a beautiful curvature effect, this plasmonic effect, and you can bring all these things together on the surface. Here we have the parabolic mirror. They have different way of the sizes of the grains are a little different, and we can actually see that. Some of the pits get enhanced more than others. So these experiments are still going on. We haven't completed it. So coming back, so like I said earlier, looking at just one approach may not work all the time. You have to have multiple. I'm not saying that polymer is a bad idea, maybe for patches and what. But if we can bring more physics into it, more physics principle, so the signals are orthogonal, they are not ratiometric, then we will be able to get a better information, like the story of elephant and blind man. So you from a different angle, you bring it together, and then you can do the machine learning will be much better, higher confidence. So people ask, what about liquid sample? You talked about vapor. What about liquid? Okay, let's start with the cantilever. So this is a cantilever. Again, we made a microfluidic channel on the top of it with a volume of 50 picoliter. You can fill the liquid, do the photothermal spectroscopy like this. This is a fumarate and glucose. Again, 50 picoliters. It is confined in it. You can also flow it if you want. And you get the spectrum. Works beautifully. We also did it with some bacteria. Basically, put some peptide inside it, send some bacteria, and then they get enriched in the sample, they get trapped. Then you can get their mass measurement, bending measurement, the energy change. You can also get the infrared spectrum of this bacteria. We can also do examples like, so once the bacteria is inside, you send some, so with some TBS solution. This is the cantilever motion, thermal motion, maybe coming from the metabolomic activity of the bacteria. Then you send some sugar solution. You can see the bacteria metabolically, and the cantilever is going crazy. And then you send the ampicillin, which is a drug that killed all the bacteria, and they are not active anymore. And so we put the sugar solution, they never came back, they are all dead. On the other hand, the same experiment repeated with the kinomycin. Kinomycin doesn't work with this bacteria. Again, PBS buffer, sugar solution, drug, and sugar solution again, and they don't say anything. So basically, it means the drug is not very good. Yeah. Oh, what about the molecular antenna idea of the for the same thing? You can spin it around in a parabolic dish. This is then that it's become a thin film. The biggest problem with infrared spectroscopy is the extinction length in the liquid. That is water. So if you make a thin film, what? So then this we tried it, but they kind of little bit is wobbling around. We have to get a better rotation. It also will work with plane surface and yeah, it's not as good as the parabolic image, but just a lens will also cut the light. So we tried that part, which was much easier. And there you go, different liquids, toluene, uh, water, spectrum. So I will address the last one and then conclude the talk. I said in the abstract, I will also talk about the power issues. So this is the sensor that we saw earlier. It was implanted in a rat sometime back. And biggest problem was that this sensor is a 8 cantilever array, piezoresistive. It works with 2 hearing aid batteries that go between them. And it's looking for the blood alcohol level of this rat. And so it's implanted in the rat. It transmits the signal it picked up by this antenna. And then, you can continuously detect it. But the biggest problem is the battery lifetime. You have to cut open the rat all the time, and the rat did not like it. You know, no? So we have to think about some other idea. So remember what Einstein said. You cannot solve the problem with the same technology that is created the problem. And you have to imagine something else. And Feynman said, okay, if you can imagine it, you should be able to make it. So if you go to Niagara Falls, you see this guy standing there, Nikola Tesla, and he came up with 100 years ago. And he said, you don't need 2 wires to do electricity. You need only 1 wire. So we can go into the theory. I don't want to spend too much time here because of the lack of time. So we did that with so these are rubber buckets, linoleum floor, wooden stick and a wire, a light bulb. This little piece of metal here, that is to reflect the ray. So this is, we made this into a AC, it's not DC, it's AC. And then getting a long-standing wave in the wire, that was a trick. And because Nikola Tesla never wrote a paper. It's all, what people said. He did it. But what did he do? We don't know. Because he never wrote it down. So we spent lots of time trying to figure it out. The reason we went after this is implanted sensor. We wanted to make an implanted sensor that does not use a battery. So we can implant it in people and then, get all the information. So let me show you, it works actually. So this is a wooden desk and aluminum foil. This is a 50-watt light bulb also. And I want to show you this is a very safe technique because voltage and current are 90 degrees off. It's connecting it and connect the light bulb and it comes on. See? So there is only 1 wire. There is no return. Electrons don't need to go home. So there is another one. It works a little bit better. So again, linoleum floor, metal desk, 4-meter top. This is insulator. It's lower. It can still go through a little bit of insulation. This we went and brought this thing from Walmart, $20 or so. Removed all the batteries, connected the motor to the leg using some wires, and then put it on this aluminum foil here, and And again, remember that it's one wire, aluminum foil, say rubber made, and it runs around. So we can actually, you don't need two wires. So our minds are basically kind of screwed up thinking that we need two wires, but there are ways we can do it with one wire. So now we have to test this out with some student, right? But it is illegal. So my postdoc now is a product in Tennessee. He connected the power bravely to his hand. Power comes on the other hand, on his hand, and he's smiling, so he's not in pain also. And moreover, we have the three kids after this. So everything is safe, right? So it works, right? So what is the relevance of this to voice learning? You can do amazing things with voice learning. Now you can bring one wire, you can change the electrical area, properties of surface charges, change the charge density on the surface. You can all kinds of bring electrophoretic forces, you can comment it. It opens up all kinds of interesting things. I think it's getting little time, so I will conclude my talk saying that in a summary, microfabrication physical sensors, you can couple with the different tools to overcome all the problems that we have seen. There is also single wire technique that we have shown. There are lots of people I worked with me in India, and Eric Chino, all these people, lots of people contributed to different parts. I'm just showing the thing here. Lots of these images are taken out of Google too, And I will be happy to